Howdy, today on Flipping Science we're going to be looking at delta H and thermochemical equations. So a thermochemical equation is an equation that shows a whole heap of information together. First thing is it needs to be balanced. So our example down here, everything is balanced. We've got our right number of chlorine atoms on this side, right number of chlorine atoms on this side, and so on. It also shows the delta H value in the proper unit, so kilojoules per mole. And for delta H, make sure you've got a positive or a negative in front of the value, and it also shows the states of all the components that are in the reaction. So AQ means aqueous, L means liquid, S means solid, and G would mean gas. So here's an example question that I picked out of an old exam. So it says one unburnt hydrocarbon, C6H6, is converted into carbon dioxide and water, releasing 3,280 kilojoules of energy per mole of liquid. C6H6. So I'm going to underline some important bits. So liquid, it tells us to start with. We're told the delta H value. We're told the bits and pieces that make it up. So complete the following equation to form a thermochemical equation. So C6H6 plus O2 goes to CO2 plus H2O. We can already put in our delta H value. We were told it's now we're burning, so that's going to be a negative value. It's going to give off energy, 3,280 kilojoules per mole. All right, we can put in our states as well. We know that one's liquid. We know oxygen is a gas, carbon dioxide is a gas, and water is a liquid. Then we need to balance. So we've got 6 carbons on this side, so that means we need 6 carbons over here. We've got 6 hydrogens on this side, so we need 6 over here, so it's already H2, so 3. Let's add up our oxygens, so 6 times 2 is 12, plus 3 is 15 oxygens, so we'll say 15 on 2 oxygen gas molecules. And there's our completed thermochemical equation. Right. This is another question from another test. So identify which of these represents these bits and pieces. So this is a separate question. Which is the enthalpy change? If we're looking at this graph here in this energy diagram, our difference between reactants and products, that's our delta H value. So that's our enthalpy change. So in this case, it's going to be Q. So that's the difference in energy between the reactants and products. That's Q. The activation energy for this reaction is going to be P up here. So this is what kicks off the reaction, starts breaking the bonds. So our answer for that one is P. Alright, on the diagram, show the reaction pathway for this reaction in the absence of the catalyst. If we go over here, so it's a catalytic converter. So in the absence of the catalyst, that means that the activation energy would be much greater. So that's all we have to represent there. Second part of the question says, hence, state and explain how the presence of the catalyst affects this reaction. Well, to start with, it's going to increase the reaction rate. The reason why it does that is the catalyst provides an alternate energy pathway for the reaction that requires less energy to occur. That means that more particles will have energy in excess of the activation energy, and that means that there'll be more successful collisions because more particles will have that extra energy. Let's look at this question now. So phosgene is produced from that reaction there. The energy released is 220 kilojoules per mole. Now it says energy released, so that tells us that it's going to be released. So that tells us it's going to be exothermic again, so we're going to have a negative value. We're told how big it is. And gases, and phosgene as well is a gas. So we know enough information now to write a thermochemical equation. So carbon monoxide, chlorine gas, it's reversible, COCl2. Now we know the state, that's a gas, that's a gas, and that's a gas. We know the delta H value. Negative because it says energy is being released, so 220 kilojoules per mole. Then we've got our states. Is that balanced? 1 carbon, 1 carbon, 1 oxygen, 1 oxygen, 2 chlorines, 2 chlorines. So that's balanced. So there's our thermochemical equation. So it's balanced, we've got our states, and we've got our delta H value. Calculate the number of kilojoules of energy released in the production of 1,000 kilograms of COCl2. Alright, First thing we need to figure out is how many moles 1,000 kilograms of COCl2 would be. So number equals mass on molar mass. Our mass is 1,000 kilograms, which is 1,000,000 grams. And our molar mass of COCl2, so we've got 12.01 plus 16 plus 2 times the molar mass of chlorine, which is 5.45, which I'm pretty sure that's what it is from the periodic table. We can shove that in our calculator and see what we get. Alright, so 1, 2, 3, 4, 5, 6 divided by 16 plus 2 times 35. So that is equal to, over here, 10110. So 10110 mole. Our amount of energy is going to be our delta H times by our number of moles. So it's going to be, delta H value from back here was 220. So 220 times by our answer. And so times 220. And we get 224, 2224, 244. 2224, 244. Now that's kilojoules. Now we should round that off to our nearest, our maximum number of significant figures. In this question it's 4, I would say. So we'll say 224 000 kilojoules, which is 2.224 times 10 to the 6 kilojoules in total. So there's some examples of using delta H and writing thermochemical equations. That's it for Flipping Science today. See ya.